session you have given us, so we know one should be lesser than, like, according to the order.
Correct. Yeah, correct.
NET questions were like pretty tough as compared to overall.
Oh, so I don't think. Let me ask you one thing, Sahil. Have you joined revision session, or have you
Yeah,
seen?
sir. I joined all the sessions, although for like NET questions for a bit of like it was dependent on, like, we have to go through all the calculations and then we have to find out that one thing. So and just putting that number into that for the answer, like, that's the thing. So in that sense, it was a little bit tough. Not that exactly, but yeah, it was.
Okay, cool.
F of x and f of y question was difficult to understand. F dash of 0 is 3 and f of 1 is 6. Would not get it at all.
Okay, so
that's and just as sir you said that 70% was covered, and just that 30% was these two questions and that sequence question.
Sequence. See, the idea behind that sequence questions, I already told you, that will be slightly difficult. You have to think a lot in that. So what you have, one most important thing you should think is, when n tends to infinity, what happens to the sequence intuitively you have to observe. So when n is tending to infinity, your terms will come closer and closer, and you will observe that an minus 1 will be equal to an as n tends to infinity. That means your previous term will be equal to the next term. As n is taking larger and larger values in your sequence, your consecutive terms will take almost equal values. So that is the thing you should observe. And when you substitute an minus 1, when you substitute an in place of an minus 1, I guess you will get, don't worry, you will get the solution, detailed solution within a couple of days, I guess. Once you go through the solution, you will understand what is the key point in that question.
Okay.
And that f dash thing we have discussed in when we are discussing activity questions. When we are in week 8, in that activity session or in the open session, in both the sessions,
okay,
we have taken the same kind of that question. It is just an activity question. So same activity question, you can see something 8.3 or somewhere. You can see the same activity question. That was actually being discussed twice. Okay. Now, it's already 2 days we passed from the quiz. So let's keep quiz aside. Let's come back to the week 10. So how many of you people have gone through week 10?
Yeah, sir, gone through
week 10. Is it easier than calculus or it is difficult than calculus?
I don't know, sir. I think both have their own things. But yeah, it's I think after doing calculus, you find graph theory a little bit easier to comprehend.
Okay. Any other inputs? Anyone would like to comment on this? I can only see 30 participants. Is the CT session still going on or?
Yes, still the CT is going on.
Right now, let's go ahead.
Okay. So, shall we wait or shall we start? I guess you are attending both the sessions simultaneously. That will be a problem because we are more or less.
No, I don't know about others. Just now I joined and checked whether this math started or not. I don't know about others what they are doing.
Okay. See, as far as me, I am not a multitasking guy. I cannot concentrate on two things at the same time. Okay, what to do? Shall we start or shall we wait?
Please take the opinion to start or not.
Yeah.
We can start, sir.
It's okay, no
Yes, sir.
issues.
We can start, sir.
Okay. Then as we are live also, I will start. So in the previous session, if you have attended that week 10 activity session, we have discussed what is a graph, What are some types of graphs? Mainly, what is cyclic, acyclic,
Yes, sir.
connected, and
Sir, can you just give a small recap of that types of graphs,
see,
sir?
if I start recapping, what happens, I will tell you. See, I have to discuss reachability, graph coloring, minimum.
Okay,
These
sir.
many things I have to discuss in this session.
No problem, sir. We can watch in that previous session.
Yeah. Just go back
Yeah,
to that
yes.
previous session.
Anyway, I
Yes,
attended.
sir, I will do that.
And these
Okay.
are anyway basic things. What is a graph? What are some types of graphs? And what is a path in a graph we have discussed. What is walk we have discussed. And we have discussed till now. And in this section, let us start looking at what is reachability, what is graph coloring. I will try to cover reachability, graph coloring, minimum vertex cover, maximum independent set matching, adjacency matrix, adjacency list, degree of a vertex. We will see what is the degree of a vertex. And later, if time permits, we will discuss BFS, DFS, DAGs, and topological sorting. Okay. If I am unable to discuss these three in the next session, maybe Vicky will take up. He will. It is a solve with the session. We'll try to complete it within 1.5 hours, and he will try to take this three topics in the next session. Okay.
Sir,
Without
I have
further.
one doubt in activity question.
Okay. Activity related to. See, whenever the topic comes up, you just ask me. You just stop me, and we will go back to that activity.
It's a like activity 10.1, sir.
Oh, okay. 10.1.
10.1 question number 4, sir.
Okay, just a second. Let me open. Okay. Question number 4.
Yes, sir.
A graph G is shown where V is the set of nodes in the graph and E is the set of edges. Correct?
Yes, sir. Yes, sir.
Okay, let me show you on the screen. Is this the question?
Yes, sir. This is the
Okay.
question.
So, okay, this is regarding reachability, right?
Okay.
Correct? Like, is this vertex V4 from vertex V4? No, from vertex V1, am I reachable to V4 or not? From vertex V2, am I reachable to V7 or not? This question. We will see in the reachability, and I will take up this question also there. Okay.
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 Or
Yes, sir.
if you are aware of what is reachability, I can answer you right away. Okay. Let me go back and start from there itself. So I guess you will be able, once I discuss this reachability, you will be able to do this. I hope. Okay. So yeah, let us start from where we left. A path is a sequence of vertices, V1, V2, V3, and so on till Vk, connected by edges. So if I have in my graph, V1 is connected to V2 with a directed edge like this, V2 to V3 like this, V3 to V4 something till Vk minus 1, and from Vk minus 1 I have an edge connecting Vk. Now V1, V2, V3, V4, V5, Vk minus 1, Vk, this is a path. So this is a path in my graph. Okay. Now what is reachability? So this term reachability is nothing but a vertex V is reachable from vertex U if there is a path from vertex U to vertex V. Okay. I say one vertex is reachable from another vertex if there is a path from U to V, that one vertex to the other vertex. So I have to try to find a path between U and V. If there is a path, then I say this particular vertex U is reachable to vertex V. So that is what reachability means. So here is an example. If a graph is given like this, so this is a directed graph. I know by now you should know what is
Yes,
directed
yes.
and undirected. So this
Yes,
is a
yes.
directed graph. You see, questions might be like, if I ask you, is D reachable from F? So if I ask you like this, is D reachable from F? What you have to do is you try to find a path from F to vertex D. If you are able to find a path in the given graph between this F and D, then I say yes, D is reachable from F.
It's not reachable.
Can you tell me, can you answer me now? This is the given graph. Is D
Not
reachable
reachable.
from F?
No, sir.
No.
No.
Yes, reachable.
No.
Yes, sir. It's
Yes, reachable from D, C, A, B, F.
D, C, A?
BF.
B, F.
Okay. So, okay, let me ask you
It's not
another simple
reachable.
question. Okay. From F, is D reachable?
You are at
No,
F.
sir.
You have
Now
to
we are
go.
starting from F.
No, sir. From F, not reachable.
Not
From
reachable.
F, not reachable. Correct?
Yes,
This
sir.
question is nothing but it is asking you, if I start from F, is D reachable? That means
No,
if I
no,
start
no.
from this vertex, can I be able to go by traversing between edges and vertices? Can I be able to go to vertex D? So let us see.
No.
No,
You see,
sir.
we are at F. There is an edge connecting F to B. So I will travel to B.
But
from B,
B,
see
nothing.
this, right? There are no outgoing edges. So these are called incoming edges. The edges which comes towards the vertex is called incoming edge. The vertex which goes from that vertex is called an outgoing edge. So here from B, there are no outgoing edges. So I can, so that I can travel. So this answer to this question is no. But what if my question is like this? Is F reachable from D?
That
Yes,
is, yes.
it is
Now I am
reachable.
at D. I am asking you whether F is reachable or not.
Yes, sir.
Yes.
Yes, sir.
Yes.
See, you can see here from D, I can travel to C,
Then A,
from C to A,
A,
and
A
from
to
A to
B,
B,
and then B
and
to
B
F.
to F. Yes, there is a path from D to F. So as I found a path, that means I can reach vertex F from D. Okay. Now there might be another questions like this. Find all the vertices that are reachable from C. So now I am at C. I want you to find all the vertices that are reachable from C. So that means if you are at C now, to where all vertices you can go by traveling between edges and vertices.
A, D, B, F.
All except E.
Yes.
A, D, B, F.
Except E. Yes.
Correct. From C I can go to A.
Yes.
From C I can go to B. That means from C to A and A to B. And
And
from
also
C I can go to
D
F.
to F.
Yeah.
And the C to D also.
And C to D also. So I
Yeah.
can travel to A, B, D,
F.
and F, except E. Correct? So I can ask you questions like this also when it comes to reachability. What if I ask you like this? Find the vertex from which every other vertex is reachable. So this is a different question. Now I want you to find one vertex such
Sir,
that
it is E.
E.
E. Sir, E.
E.
such that every other vertex is reachable.
E.
That means if you stand at some vertex point, from that vertex point I should actually able to travel to all other vertices. Which vertex is that?
B. It is E.
E.
Vertex E, sir.
E.
Vertex E, sir.
Correct.
E is also reachable.
So only E, or are there any other vertices also?
B also.
B.
No, sir.
F. No,
No,
sir.
sir. Only
No,
no,
no.
sir.
B,
Only
we
not
cannot
Only
go
E.
anywhere.
Only
Yes.
E.
Okay. Let us
Only
see. Let us pick. You can check it quickly. From F, will you be able to reach every other vertex?
No, sir.
No, sir.
No,
From
sir.
F, you can only able to go to B.
B.
B. Yeah.
So you start. Now let's take D. If you are at B, you can go to F. Correct.
Yes,
You
sir.
are at B.
Yes,
You
Yes,
can
sir.
sir.
only
Only
able to
F.
travel with this vertex,
Only F.
with this
Yeah.
edge, and you can able to travel to F only. You cannot travel to every other vertex. Okay. From A,
B and
A.
F.
We can go to
F.
B.
BF.
B, F.
from A, you can go to B. From B, you
Yeah,
can
B.
go to F. That's
F.
it.
Yeah.
So you cannot travel to D, C, and E. A is also ruled out. So B, A, F. What about C? From C, can I able
C.
to go to
A,
E?
B.
C to
No,
A. C to D.
we cannot go to
Can't
E
go to
from
Except
E,
E.
But
sir.
we cannot
Except E.
go
Just
to
now we checked,
E.
right? Except
Yeah,
E, we
yes.
can go to every other vertex.
Every
But
other.
we are not able to go to E. So even
Yes, sir.
C is not. C does not satisfy that condition. Whether D, whether this vertex D,
D.
We were
The
We
same
cannot
accepting.
go
thing.
to
No,
Except
sir.
E,
Can't go.
we can
E.
E.
go.
We cannot go.
correct.
So
The same thing for same thing. What happened to C? The same
the
applies
same
to
for
D
D
also.
also.
Even D cannot visit. So all these are failed. So E, when you come to E, from E you can actually travel to D. From D you can actually travel to C. From C to A to B, B to F, or
Yes,
from
sir.
E to B, B to F. So you can cover every other vertex, or you can find a path from E to every other vertex in the graph. Correct. So yeah, this is about reachability paths. So reachability by implies path. Why I said this by implies means if you have a path, then that vertex, one vertex is reachable from another vertex. If one vertex is reachable from another vertex, then there is a path between those two vertices. So this is an if and only if condition. You can. Okay. So this is about reachability. Now coming to the 10.3 question. Now everyone answer this question now. So there is a graph given like this to us. Let me zoom this. So is the graph visible?
Yes, sir.
Yes, sir.
So this is a graph given to you now. So there are some 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 vertices and some directed edges. So tell me from option A and B whether it is directed or undirected.
Directed.
Directed graph.
Directed graph. Okay, so option A is incorrect. Option B is correct. Correct. Now option C is V4 is reachable from V1, V2, V5. That means from V1, V4 is reachable. From V2, V4 is reachable. From V5, V4 is reachable. Is this true? Just check from the
Yes.
option.
Yes, sir.
Yes.
Yes, sir.
Yes.
So you can
Yes.
see here from
Yes,
V1 I
Yes.
can actually come to V0, and from V0 I can actually go to V4. Same thing
V4.
for V2 also. V2 to V0, V0 to V. And also where is V5? V5 to V4. So I can actually find a path from V1 to V4, V2 to V4, V5 to V4. So this is also correct.
Okay.
So what is option 4? V4 is reachable from every node. So yeah, just
No,
check.
sir.
So whether V4 is reachable from every other vertex?
No, sir.
No, sir.
No,
No.
sir.
V7. V7.
B5.
V7.
V8.
Correct. V8. You
V
take V8. Simple
Yes.
V8.
V8 and V7, sir.
Are not reachable.
V5 also.
Even V3
V5
also.
is.
V5 reachable.
See, the question is V4 is reachable. From every node, is V4 reachable or not? You should check.
If from V3, it's not reachable.
Correct. From V3, it's reachable. V3 to
It's
V6,
reachable, sir.
V6 to V3.
Reachable.
It is reachable.
V3 reachable,
Sir,
but
from V8, from
V8
V7.
and V7.
V7.
Correct.
From V8, there is no direction at all. It's
yeah,
stopping.
V7 and V8.
So
V8.
from V8, you travel to V7, but you
Yes,
should
but
Yeah,
end
don't
at
have
there.
any out this
yes.
thing.
Correct. So that means there are some vertices
And
from
V6
which you
also.
start. From where you start, you cannot reach to V4. Correct. That means this is wrong. V7 is reachable from every node. That means if you start from any node, you should reach to V7. Is this
Yes,
true?
sir.
Yes,
Yeah,
sir.
it's correct.
Yeah, this is true, sir.
Yes, sir.
You can check. You
Yeah.
start from every other vertex. You start from V1. You check whether there is a path to V7 or not.
Yes, sir.
You
Yes,
start from
sir.
V2, check a path. V0, check the path. V5, check the path. V4, check the path. V3, V6, V9. Similarly, V8. So you will get, once you check, you will obviously get from anywhere you start, you can actually reach to V7. That is what you will get from this option. So that means this is reachable. Now the last option is only V7 is not reachable to V4.
V8 also.
Now tell me,
V8
it
and
tells
V8
that
also.
both
correct.
both.
Reachable from all, that is not the correct condition.
False.
What
It's
is that?
false.
Only V7 is not reachable to V4.
False.
Is this
Every
correct?
node, then V4 should reach it.
False, sir.
That is not correct.
False.
No,
False.
V4, it's not, you are at now V7. It is saying that if you start from V7, you cannot reach to V4. Only V7, if you only start from V7, then only you cannot reach to V4. Every other case, you can reach to V4. That is what
From
it says.
V8 also we cannot reach, no?
7 is not reachable to V4, right? V7 is reachable. That's the question here.
V7
V7.
reachable
No,
to
no, no.
V4.
Only
No.
V7, last one.
Only V7. This thing. We are talking about the last option. We are talking about the last option. We are done with this option.
The reachable is for V7 or V4. It looks like the question looks like it talks about if V7 is reachable by V4 or not.
No, it's not by 2.
It's the other way around.
Yeah, it's the other way around. From V7, whether V4 is reachable or not. If not reachable, then V7 is the only vertex like that. V7 is the only vertex that is not reachable to V4. That means you cannot find a path from V7 to V4. From any other vertex, you can find a path to V4. That is what this statement tells you. This only thing tells you that only V7 is that kind. But if you see from V8 also, you cannot reach to V4 from the graph.
Yes. That's why it's false.
So that is why it is false. So now only options are B, C, E. Okay.
Okay.
Yeah. So that is about
question 3 in that.
question 3 is something related to non-simple graphs. So the simple graph means there are no loops and kind of thing. Okay, let me take that thing also. Many of you have asked. Okay, this says an electric wire having a resistor can be represented as an edge of a graph. That is, a resistor is equivalent to 2 nodes connected with one edge. Okay, this particular resistor means this is an edge with 2 nodes here.
Excuse me, sir.
The screen.
Sir, screen, sir. Question is not visible.
Okay. Sorry, sir.
I thought mine was lagging.
Okay, sorry. Is it visible now?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes.
Okay. Now, what it tells us is a resistor can be represented as an edge of a graph. That is, a resistor is equivalent to 2 nodes connected with one edge. See, this is a resistor here. This thing is a resistor here. So this particular thing represents 2 nodes with one edge. So like this. So this is a node. This is node with one edge represents this resistor. And there is another resistor. That means there is a node and another node with one edge. So node with one edge. Okay. You try to get that. So end points are the nodes. End points of the resistor are the nodes. And between this zigzag is the edge. Okay. Once this graph can be drawn like this, we are asking you which graph will look, which graph will be formed after drawing the, after converting this graph to the vertices and edges. So now you see there are 1, 2, 3, 4, 5, 6. 6 resistors.
Six edges.
Six edges. So your graph should contain 6 edges. Okay. So from that itself you see 1, 2, 3, 4, 5. Option B is false because option B has only 5 edges. 1, 2, 3, 4, 5. 5 edges. 1,
Sir,
2,
option
3.
1. No.
Option 1.
Option 1.
Only option 1 will satisfy the required condition. Okay. And you can draw this graph actually. You keep this as a node. You keep this as a node. And this becomes one node. And this becomes another node. And this becomes another node. 1, 2, 3, 4, 5. 5 nodes. 4 nodes. Okay.
Can you
Sorry,
scroll
this
up?
whole will become another node.
Sir, can you scroll up?
Up this here.
Yeah.
Okay.
And if there is no register, it will be considered as only one node. What it means?
Yeah, only one node. This thing is actually, this is a long connection, but you can short it out. So between two resistors, there will be a node. Okay. Here also you see resistor, resistor, and a resistor. These all are connected through a wire, and this particular thing will become a node. Here also this will be the node. This will be the node, and these 3 resistors are connected to this node. So there will be 4 nodes, 6 edges.
Yes.
So from the graph, if you observe from the edges itself, it is sufficient. The rest of the 3 options will rule it out directly.
Are we going to apply Kirchhoff's current laws on this?
Nothing. Good one. No. Okay. So this is about reachability. So let us see what is graph coloring means. So in the lectures, if you go, there is a detailed explanation of what graph coloring is. Graph coloring actually professor has discussed in terms of functions. But I just wanted to make it very simple, clean. You just watch the lecture, go back, watch the lecture. If you are unable to understand, then come back to this session, follow this method. So graph coloring is basically, you have to find the minimum number of colors required to color every vertex in a graph such that no two adjacent, see when I say adjacent means sharing an edge. If two vertices shares an edge, then we say those two vertices are adjacent to each other. So this is simply, you have to give one color to each vertex such that the vertices which shares edge between them shouldn't take the same color. So that is what graph coloring means. So how do we proceed and how do we find the graph coloring? So one approach is you start from any vertex. You take one color, you start from any vertex. So let us take blue color first. So which vertex will we take? You give me any vertex.
A.
Vertex A.
A.
Start with A, yeah.
Okay. So once I am giving first color or blue color to vertex A, I am not supposed to give the same blue color to C, D, B because these are adjacent vertices to A.
E will get blue color. G will get blue color.
Yeah. So you cannot give C, D, B the same color. You choose the vertex which can be given blue color. So E, F, G can be given blue color. So which vertex? Choose any random vertex.
F.
Because E and F become adjacent to each other. So.
Okay.
Palkasirkya.
So we choose F now.
So in this question, minimum number of colors. So we took E and G instead of.
That will not matter. You can
Someone please mute.
Please try to mute. I'm just muting you.
Sir, I think better we go with coloring E so that we can color G or blue color. Give.
Okay, fine. Oh, fine. In that case, nothing changes. But okay, it's better to give color to E. So try to give maximum number of vertices the first color. So that will be a better idea. So similarly, we can color blue color to G.
So, sir, I didn't get that. First we colored F, then why we went to E, why it was a better choice.
See, why I went is personally in order to have 100% surety about the coloring. So 99.99% cases it will work. Whatever the vertex you choose, it will work. Maybe you will give blue color to three vertices and red color to two vertices. And in other case, maybe you'll give blue color to two vertices and red color to the three vertices. Three. So it's a vice versa kind of thing. That's it. But why I started giving maximum color to the first color is because to avoid any complications or such. Okay, it doesn't matter. Even you can choose F also. Okay, then E and G will take another color, and C, D, B will take another.
I guess F will get a unique color.
Yeah, F will definitely get a unique color. Okay, now can I from this C, D, F, B? Is there any vertex that I can give blue color or the first color to it?
No more.
So that this condition satisfies?
No more.
No, right? I cannot give to C, D, B. I cannot also give to F. Now I will change the color. I will bring the second color and I will choose a random color. Which one?
Option vertex C.
All adjacent ones we can take. C, D, and B will all get red colors.
Okay. C will get red. D will get red.
And B.
And B also I can give red because there
Yeah.
is no red colored vertex that is
Adjacent to that.
Okay. Now can I give red color to F?
No, sir.
So choose another color, a different color, green maybe. So the new color F. Now that all the vertices are color. So how many colors we used?
Three colors.
Three colors. So the graph coloring or the vertex coloring or simply the coloring means the coloring of this vertex is 3. So the vertex color of this graph is 3. So that is how we try to solve questions related to graph coloring. So this is what graph coloring means. We try to give colors to every vertex such that no two adjacent vertex gets the same color, and we try to minimize it. Okay.
So is there any particular importance of this concept? Only
Of course, a lot. See, graph coloring is a key topic in graph theory. So see, even in your graded assignments or practice assignments, we have given you many questions that involves real life scenarios where we use graph coloring. So one such is in the lecture also sir has explained, if you are trying to schedule few events so that some events have same coordinator or something, so that they shouldn't overlap. So you have to come up with a schedule. In those kind of scheduling things, we definitely use this graph coloring, and we will try to come up with the least time required so that we can schedule all the events.
Okay. Got it.
In video, it explained with map, Indian map.
Yeah, Indian map also. So those are planar things. I don't want to bring planarity in this lecture. Okay. Anyway, graph coloring has an lots of importance in real life also. So one thing, so very few things that can be related to anyway graph. If you wanted to study graph theory, there are few topics which you have to definitely study and understand it very cleanly. In that, one important one is graph coloring or vertex coloring. So why we say vertex coloring? Because there is edge coloring also. So that is unnecessary too. And nowadays researchers are going on fractional coloring. So yeah, see, if there is no importance, people will not research on this further. Okay. So as of now, I can recall on this scheduling thing only. So if you wanted to schedule more number of events within less time, graph coloring will definitely see. If you have 8 events and you have only 2 hours, and you have to schedule it properly within the 2 hours, and some said actually you can schedule it within 2 hours and you might not be able to get that. How? Maybe he used graph coloring techniques and find out that all the 8 events can be scheduled within 2 hours.
Got it.
Okay. Okay, this is about graph coloring. So there is another important kind of topic. This is very important when you are studying only graph theory. So when you are studying 4 weeks content of graph theory, then this vertex cover is more important. When in optimization things also, it is very important. So what this minimum, why minimum came, what is this vertex cover, we will say. So this vertex cover is basically, we should find the smallest subset of V. So let's say V prime. So I am going to take the subset of the set of vertices such that it covers all the edges in the graph. So covering an edge means I should choose either one end of the edge, at least one end of the edge. So if I say, if I have 2 vertices, if I choose this vertex in this V prime, then I can say that this edge is being covered with respect to this vertex. So I should choose any one of the vertex from each edge. And also on a whole graph, I should choose very less number of vertices such that every edge is being covered. So if you see, if I choose this C vertex here, so I am choosing, okay, now that we know that V prime is nothing but the subset of V. So it should be anyway subset of this set A, B, C, D, E, F, G. So this is the set of vertices we have, and V prime should be the subset of this. So how do we start is, for this what I suggest is you choose the vertex which has more number of edges that are connected to it.
F
So
and C.
which vertex is this?
F, sir.
F. Yeah.
F.
F.
I guess E.
Yeah, F or
No,
E.
yes, yes,
Yes,
yes.
sir.
Okay. You can
E
choose
and F
E.
both.
You start by choosing E. Okay.
And F have the same number.
So if you choose E, see here, I have chosen E. So that means this edge is covered, this edge is covered, this edge is covered, and this edge is covered. So 4 edges has been covered with vertex E. Now I again also have to cover this edge, still I have to cover these many edges. So now
choose A, I can.
Yeah, now choose A. So I choose E. Now choose A. So once I choose A, this edge is being covered, this edge is being covered, and this edge is being covered. Now again I am left with this edge, this edge, this edge, and this edge. 4 edges need to be covered.
F and G or the next.
F.
You take any one of it. F. You choose F. So once I choose F, I add that to V dash. So now this edge is covered, this edge is covered, and also this edge is covered. So only edge that is left is DG. So choose any of the vertex so that it covers. So what shall we choose?
Either D or G.
G is fine.
Okay, you choose any of them. G is fine or D is fine. Okay. Okay. Now we have chosen EAFG, which is a subset of the vertex set. Now what my claim is, this is the minimum vertex cover. See, you can see from the terms itself. So minimum number of vertices I am choosing to cover all the edges. So EAFG, I should at least choose 4 vertices such that every edge is being covered. Okay. So I will tell you why this why you have to always start with the always vertex with the most number of edges connected to it. Let me give you another same graph, another set you might end up with.
So this is independent set when
No,
we
this is not independent set. This is minimum vertex cover. So you can see here E and F are connected with an edge. Okay, E is there in my set, F is there in my set, but E and F are connected by an edge. This is not an independent set. Okay, look at this thing. D prime star. So I started from C. Okay, I started from C, and again I choose FG, FGB. See the C to cover this edge. Now you see, if I choose C, this edge being covered. If I choose F, this edge, this edge, this edge, this edge is being covered. And for this edge, I am choosing G. If I choose G, this edge is being covered. Next, I have to choose. I still have to cover EB, AB, AD. These three edges are left, and then I can choose B to cover these two edges. Now I am left with, I already got 4 vertices, CFGB, CFGB. Still I have to cover this AD edge, and you might end up taking A or D. A, maybe A. Now you see, this particular green highlighted thing is also a vertex cover, but this is not the minimum vertex cover. So even this particular set V1 star covers all the edges, but this particular V1 star is not the minimum vertex cover. You have to find the smallest subset. This cardinality of this subset is 5, cardinality of this subset is 4. This is smallest than this.
Excuse me, sir.
Yeah.
So instead of G, if you would have taken D,
and
yeah,
then you can, that is also one good what we can say as one good C, D, F, D. Okay, yeah, this is also a vertex cover, minimum vertex cover. So I don't say there is a unique minimum vertex cover. There can be many vertex covers that are minimum, but I just wanted to make the difference between the vertex cover and the minimum vertex cover. So the CFGBA is also a vertex cover, and also this whole vertex set is also a vertex cover, but that is not the minimum. Okay. So why we always, my question is, why we always go to the minimum vertex cover? Why the minimum?
Sir, in the
So
lecture,
that I think it can have many real life examples. Suppose one
see
cover.
minimum.
solving the real life examples easily.
So if you people know
If you want to
PNP
cover
hard,
size,
NPP, then you might know this vertex cover plays a very key role in solving many of the problems. So in making decision whether that problem is solvable or not can be found out by this minimum vertex cover. So that means if I have given you an unsolvable problem to you, so if I say something which is not solvable at all, I have given you and I asked you to solve this, and the thing is, it turns out to be that it may be unsolvable problem, and you keep on trying that until you die. So in order to, there are many problems which will fall in this NP hard kind of thing, NP problems we say, that cannot be solved in the given time. Okay, how much ever time I give you, you cannot able to solve that. So in order to find whether those problems fall under that category or not, this particular minimum vertex cover plays a key role in optimization things. So even in optimization, this vertex cover is very important. So as of now, you don't need to worry about that lot, but you just understand what the minimum vertex cover is. Our questions will always be simple. We will give you, maybe we will give you the graph. We will try to ask you what is the minimum vertex cover of that, or we will give you some application, some real life application of it. We will try to bring it out. You just have to identify. You should find the minimum vertex cover. That's it. So every question will lie in this category only. There will not be any hard problems. Okay, so this is how you find vertex cover. Also start with the vertex which has more number of edges that are connected to that vertex, and same applies. I add that vertex to your vertex cover, and you move to the next you move next. In the same case, we try to find maximum independent set. So you see, observe, minimum is the optimal thing for vertex cover, and here maximum independent set is the optimal for independent set. So here you see independent set starts from one vertex, and we in any given graph, this particular what independent set is, you find the largest subset of V such that no two vertices in this V prime are connected by an edge. So you have to find some vertices such that if I choose any two vertices in that V prime or in that independent set, there should not be any directed edge connected to it. Okay, that is what the maximum independent set means. It is a set which is a subset of vertex set again, but now what should be the condition is, whatever the vertices you choose, among those vertices there should not be any edge connecting between those two. So that particular set is called independent set. Now the optimal situation in this independent set is, we try to find the maximum number of vertices that satisfy this property. So you see in this graph itself, only vertex C, if I choose only vertex C, it's an independent set. So you see only one vertex if I choose, that's an independent set. Or I can choose some vertex C and vertex D. So there are two vertices in my set V prime, V1 prime, sorry, V1 star. So in these two also, C and D are not connected by a direct edge. So I can say this is an independent set. So like this, if I try to find, or if I try to maximize, that is what the optimal case we say. You try to maximize, we will see how many number of vertices I can bring into this particular set, so that if I choose any two vertices, there will not be a direct edge connected. Okay, from this graph, now tell me what vertices can I choose so that that particular set will become the maximum independent set.
Sir, either C, D or B or G, B or A. G, B, A, C, D, B.
C, D, B.
One more there is, sir.
C, G, B.
G, B, C. Yeah. D, B, C.
Oh no, no E.
D,
A, F.
D.
No. If I involve
CBD.
CBD has been okay.
AEG.
AEG.
Okay. Yeah. See, there again, there can be many maximum independent set. What we ask you is, what is the cardinality of maximum independent set is the primary question we might ask you. But if you try to find the interconnection between vertex cover and maximum independent set, that will look more satisfying to you. You see, when you find a minimum vertex cover, here, if you see, if I take E, A, F, G, this vertex cover, what all the vertex left out from this V prime forms an independent set.
Can you please repeat the statement, please?
The statement is, when you find the minimum vertex cover or minimum vertex cover set, if you have the minimum vertex cover set with you, so the vertices which are left out from this V prime will form an independent set, and that will be the maximum independent set.
Okay.
So you can see EAFG is a vertex cover which we found it. EAFG. Now the left out vertices are CBD. Now the CBD forms a maximum independent set. So the connection between this maximum independent set and vertex cover is, if I have vertex cover set as VC, the cardinality of VC plus the cardinality of VI will be equal to the cardinality, total number of vertices in the graph. So the minimum vertex cover is 3 in an 7 vertices graph. Then the maximum vertex, maximum independent set will be 4. The cardinality of maximum independent set will be 4. And once you have the minimum vertex cover set, the complement of it will be the maximum independent set.
So what is VC?
VC is just the
vertex
so
cover.
Here this V
minimum
prime,
vertex.
I just denoted it as vertex cover set.
Can
Minimum
mutually-
vertex cover set.
Can we say it mutually exclusive?
It might not.
That is statistics.
It will not always be mutually exclusive. See, EAFG. Here also, if you take the maximum independent set to be CGB, now G comes in both cases, right?
Yes.
Okay. So remember, not remember. You can try to interpret this. This is very easy to interpret. So once you find the vertex cover, take any graph, you find the vertex cover, minimum vertex cover, and the left out vertices will actually give you the maximum independent set. Okay, this is minimum vertex cover.
Is there a mathematical way of finding this out?
Yeah. There is a mathematical proof. Mathematical way of finding
Cover set, the smallest subset.
This vertex cover, minimum vertex cover.
Minimum vertex cover. Is there a mathematical way? Is like a formula or something like that?
No. See, in fact, I just brought this NP hard thing, right? Unsolvable problems. This vertex cover is basically falls into unsolvable problems.
Unsolvable. Okay.
Okay. Yeah.
Okay.
So whatever the problem I give you, you try to convert that problem into this vertex cover. You try to convert that problem into this. If you are able to try to convert that problem into this vertex cover kind of problem, then you say this problem is also unsolvable. That is how we
Oh,
whether this problem is
okay.
solvable or not.
Okay. Transform a problem into an unsolvable. If a problem, transform it. Okay.
Right. So you don't need to get into those things, but there is no solid way. There is a proof that it is unsolvable. This vertex cover we cannot solve in the given time. Okay. Now that these vertices are only 6, 7, 8 till 10 till 20 is also a small graphs. What if your n is very large, like maybe some 100 or 200? Then it is very difficult and it is unsolvable.
That is the reason why I asked if there was a mathematical formula behind identifying the smallest set. So
No. So to this course, we will stick to a graph which has only some n equals to 12, lesser than or equal to 12 vertices.
Okay.
So with these given vertices, we can actually find, by using some permutation and combinations, we can actually find the minimum vertex cover.
Is the minimum set is null set for VC and VI? Is there any possibility?
Null set? No. See, how can that be null set? If there is no edge in your graph, then the minimum vertex cover is null set.
But in minimum vertex cover, everything should be covered, right? If
every edge needs to be covered.
Yeah.
It will cover for sure.
Okay. So even though if you have one edge in your graph, at least either one of the end point vertex should be in your vertex cover, which makes the vertex minimum vertex cover is not a null or phi. Okay. So this is.
Can you please repeat in a minute what was maximum independent set? I lost my internet connectivity for a few minutes.
Okay, maximum independent set is you should choose some subset of vertices such that in that maximum independent set, if I choose any two vertices, that should not share an edge in the given graph. Now if you see CDB, this particular vertex CDB, C doesn't share an edge with D, C doesn't share an edge with B. Similarly, B doesn't share an edge with C.
Okay.
D doesn't share an edge with D. And also, I can only find 3 vertices. There will not be any fourth vertices, so that I can bring it into this vertex independent set and claim it as the maximum independent. Independent, look it like this. Independent means the vertices are
They
not
not
connected.
with each other. Okay.
Not connected with each other. So whatever the set I choose, they should not be connected to each other.
Okay.
Okay,
Similarly, CGB is also not connected and AGE is also not connected to each other.
Yeah, AGE also not connected to each other. These are all maximum independent sets to this particular graph.
So while finding for example, in every set there are 3 elements. So whichever is the set which has got maximum number of vertices, that we'll consider.
Correct.
Okay. So here all the sets contain 3, so 3 becomes by default the set, right?
Correct. See, you can have CD also. CD also doesn't share an edge.
Okay.
Okay. This is also an independent set, but this is not the maximum independent set.
Okay. Fine.
Yeah.
Thank you.
Okay. So this is maximum independent set. So now comes matching. Now till now we have trying to find the subsets of vertex set, right? Now what this matching is, now this particular matching plays with subset of edge set. So if you have some E edges in your graph, we try to find the subset of edges such that all the edges in this newly subset E prime are disjoint. When I say disjoint, this means there is no common vertex to both the edges. No common vertex. See, this particular edge and this particular edge has a common vertex B. So this edge and this edge are not disjoint. So we try to find the disjoint edges and we try to find the maximal. Okay, let me explain what is the difference between maximal and maximal. So there is a lot, the maximum. So any one of you know what is the difference? Okay, so maximal means if I add one more thing to that, this set, maximum set. So if I add one more element to this set, then it fails the property of that set, or the condition is going to fail. So I cannot add another element into this set, but this is not the maximum. But there is another set that might be the maximum. Understand this in this way. So let me tell you in the example kind of thing itself. See, in this particular thing, what I should come up with the subset of edges such that all the edges I choose should be disjoint. So if I have chosen this BE edge once, what edge can I choose which is disjoint to BE?
Only AF.
Only
AF.
Correct. So now my this matching to this set, matching set M is this edge AF and B. So if you observe, this is not the maximum matching. This is not the maximum matching. Why? Because this is not the maximum matching is I can find another subset.
Yes, sir.
Such that I will have more number of edges into my matching set. Okay, but this is maximal matching. This is maximal because I cannot add one more edge to this set. So AFB with this two edges, I cannot add one more edge to this set. If I add one more edge to this set, the property breaks. The property of this disjoint breaks. So this is maximal matching. And if you see this thing, so AF.
So if we take
Yeah.
AB as a particular
So
line,
it's
then
BC
that will
and
have
ED.
BC and ED, yeah.
Yeah.
See these things AF, BC, ED. So this particular AF, BC, ED. So this is maximum matching. So understand the difference between maximal and maximum. So in this course, we are worrying about the maximal. If you can come up with the maximal, it's sufficient. Okay, no need to be maximum.
Means minimum. Minimum
Sir,
matching.
can you explain it
No, it's
one
not
more
minimum
time?
matching.
Yes, can you sir explain one more, please?
One more
Okay.
time.
Okay. So matching is actually you try to find the subset of edges so that whatever the edges I choose, those should be disjoint. Okay. If I start choosing from, okay, if I E prime, if I start choosing, I have 1, 2, 3, 4, 5, 6, 7 edges with me, and I have to choose the subset of these edges. So among these 7 edges, I choose AB as my first edge. So once I choose AB as my first edge, I cannot choose AF into my matching set because these two are not disjoint. Similarly, BF also I cannot add because AB and BF shares a vertex. Similarly, BC, BE. So these 4 edges I cannot add if I add AB into my matching set. Okay, I ignored all these 4. Now I can add either CE or ED. So add one of it. So now we are adding CE. So once I add CE, so I have added AB and CE into my set. Okay. So can I add one more edge so that now if I bring that edge into this set, then these 3 edges will become disjoint. These 3 edges should be disjoint. Disjoint means they should not share a common vertex. Is there any other edge other than AB and CE?
So that means even CE should not have any matching edge with others? That
That
condition
means
holds
CE
for
also
CE
should not
also?
have any matching edge. No?
Okay.
Now I cannot add actually, right? So this is the maximal number of edges I can add into this E prime. So this E prime is nothing but the matching here. So this
But
particular
normally
match.
what we write maximum set is this only. No? Regularly we'll say maximum.
What
minimum.
can you be little louder, please? What is?
Normally maximum we should write. Maximum minimum we are writing in mathematics. That is also same maximum only, no?
No. See, if this is maximum, I will give you another set. Consider this set one. AF, BC, ED. The cardinality of this set is only 2. What is the cardinality of this set?
3.
3. So which one is maximum?
AF.
Maximum.
3 is
Maximum.
maximum.
This is maximum.
Yes.
Yes. Yes.
Okay. So
Yes.
this is maximal is nothing but if I add one more element into this, that breaks the condition or that fails the property of what we are trying to find.
Sir, if we select B, then
But both are minimum. Sorry, maximum.
Yeah,
But
both are
Both AF, BC, and that one is also is maximal, right?
Correct. This is also maximal.
Okay.
Okay, this is
sir, if we
maximal.
select B, then if I select B, then no, I can't select BE.
BE, yeah. If you select BE,
then I can't select any other.
You can select AF, right?
Yeah. Sir.
So AF is also the maximal.
Maximal.
So we are only going to get 2 edges, right? So there is another set I can find where actually it contains 3 edges. So even that is also the maximal, but that is also maximum. So whichever has the highest number of edges, so the largest number of edges, that is called maximum. And whichever the set has some edges, some number, and if I add one more element into that, if the property is failed, that is called maximal.
Something like global maximum, global maximum.
Okay, if you able to understand it in that way, it's okay.
What is the matching set here? Which one is?
Everything is a matching set.
The maximal is something after taking these two, we can't add any one more set.
One more edge into that set. So
yes.
That is the maximum.
All 3 are matching only. Maximal set only.
These all are matchings only.
Maximal subsets.
Maximal matchings.
Okay.
So how do we visualize a question in this concept? What kind of questions can we solve in this?
Okay, you do see this involves much more complicated kind of question. So in the lecture also Sarah has discussed something called if you are doing a project, so if you have to do it alone, or if you are doing with 2 people, you should be friends. So just go back to that lecture. Those kind of cases, some complicated kind of cases, this matching comes. So as of now, don't worry much about matching. Just worry about vertex cover, maximum independent set, and don't go in deep of these things. So if a graph is given, are you able to find minimum vertex cover, maximum independent set, or the matching of the given graph or not? Worry till there.
Sir, can you scroll up? What happens when the graph is complete graph, max independent set?
Okay. When it is complete, max independent set will be 1. Minimum vertex cover will be n minus 1.
The condition you have given that there, the v dash plus here vc dash vc plus v1 vi.
Correct. Yeah.
It should only minimum vertex. It will be 1 na. It will also 1 na. Minimum
No.
vertex cover.
That is minimum vertex cover na. You take 4 vertices. This is the complete graph, right? So minimum vertex cover is you have to cover all the 6 vertices. So if I choose A in my vertex cover set, I covered this. Still I have to cover 3 vertices, 3 edges. These 3 edges need to be covered.
Yes.
Okay, if I choose B, then this and this is covered, and I still have to cover this vertex, this edge. So I have to choose C or D. So the minimum vertex cover will be 1 less than the number of vertices.
Number what? Yes.
Okay. So this is maximum independent set. Matching, you don't need to, that is what I said. No need to, that is why we gave you the maximal subset. Just try to find maximal. No need to look for maximum. How you find this? You take one edge, you remove all the other edges that are joined to this particular edge that shares an edge with this particular edge, that shares a vertex with this particular edge, and you take the another edge which is disjoint to that particular BCA. Okay, like this you try to come up with the maximal subset. It is comes with maximal subset. So this is what matching is. Perfect matching means all the vertices need to be covered. So now you see AF, BC, ED.
Maximum matching.
BC, ED. Now this is a perfect matching. Perfect matching means every vertex is being covered. So A is being covered, F is being covered, B, C, E, D. Every vertex is being covered in this matching. This is also called as a perfect matching. So 3 names for this. And perfect matching exists only for the graphs which has even degree vertices. Sorry, even number of vertices. Okay. So that is what that is
Sir,
about
even
matching.
number of what?
What was that, sir, again?
That thing is see, perfect matching is exists only for even number of vertices. If your graph has some 5 vertices, you cannot come up with the perfect matching. So if your graph is having like this, if your graph is like this, in this graph, in this particular graph, if I try to find the perfect matching, remember what I said about perfect matching. Every vertex need to be covered. Okay, if I choose this particular edge in my matching, and I can choose this particular edge in my matching. Now, if I choose these 2 edges, I cannot choose any other edge. And this particular vertex will always be left out. So in an odd number of vertices graph, every time, see, even in normally you see, if you in your classroom, there are odd number of people sitting in the classroom, and the teacher asks you to pair up. Every time there will be one guy left out if it is an odd number of people. Right?
Right, sir. That's a good analogy.
That's the okay. So perfect matching exists or perfect matching you can find it only for the graphs which has even number of vertices. Okay. Okay, let's move a little forward. Now let us talk about degree of a vertex. So the degree of a vertex in an undirected graph. So observe this. We are now in undirected thing. So degree of a vertex is different for undirected and directed. We will discuss both. Degree of a vertex I, some vertex I in a graph G, in an undirected graph, is the number of edges that are incident to the vertex I. This incident means that are, maybe you can say that edge, one endpoint of that edge is that vertex. So if this is the edge, this edge is incident with B. That means this particular edge has endpoint B, one endpoint as B. So that is what incident is. Okay, adjacent, incident, these are all terminologies of graph theory. Okay, so you just have to count the number of edges that are actually connected to this vertex. Now quickly tell me what is the degree of, this is an undirected graph. What is the degree of vertex C? So you just have to find the number of edges that are connected to this vertex C.
2.
Correct. This edge and this edge. So the degree of vertex C is 2. Similarly, what is the degree of F?
F also 2.
2.
A?
2.
A also 2.
D?
4.
D.
4. D only 1.
1.
E?
E 3.
3, 3.
D?
B also 3. No, 4, sir.
4.
4.
Correct. So you just have to, if this is an undirected graph, you just have to count the number of edges that are actually connected to that particular vertex. Okay. So whatever the graph may be, this is how you find the degree of each vertex. So depending upon the question, if you ask you what is the degree of C, what is the degree of F, what is the sum of all the degrees of the given graph, the sum of all the degrees of vertices in the given graph. So you just have to add 1 plus 2 plus 2 plus 2 plus 3
14.
Yeah, 7 plus 6, so 13, 14. Correct. Okay. So this is how you try to find the degree of a vertex in an undirected graph. What if it is a directed graph? If it is a directed graph, now each vertex will have in degree and out degree separately. So till now we have only one number associated with this each vertex. But now if it is directed, we will have two numbers associated with every vertex. One is in degree, another one is out degree. So this is how it goes. See, in degree means number of edges that comes towards the vertex. Okay, incoming, we say incoming edges. Simply incoming edges. Number of incoming edges. Okay, so this is number of outgoing edges. So every vertex will have number of incoming edges. Every vertex will have number of outgoing edges. Let us compute in degrees of every vertex in this graph. This is a directed graph. Now tell me number of what is the in degree of B?
2. 2. 2.
You see, this edge is coming towards me. This edge is coming towards me. So in degree of B is 2.
2.
What is in degree of C?
2.
2. So only two edges coming. Only two edges are connected to C, and those two edges are incoming edges. So in degree of C is 2. What is in degree of D?
0.
0.
0.
What is in degree of E?
3.
Is 3.
Right. You just have to check number of incoming edges. What is
1
it?
out degree.
For F?
2.
2.
2.
For A?
G.
No, 0.
0.
Now out degree. Let us compute the out degrees also. Number of out degrees for A?
2.
2.
B?
2.
1. 2.
Sorry, 2.
2.
2.
See, here one, here another.
Yeah.
C?
0.
0.
0.
D?
D1.
1.
1.
0.
E1.
1.
Sir,
1. 1.
F1.
F?
1.
F also 1.
Correct. So this correct. So red represents out degree and blue number represents in degree. So we have two different degrees for each of the vertex in a directed graph case. And remember, this is not true. A strong note. Degree is equal to in degree plus out degree. This is not true. There is no degree of a vertex when it comes to directed graph. Okay, there is a separate in degree and there is a separate out degree. So it doesn't imply that degree of this particular vertex is 2 plus 2. Like in this case, there is no degree of vertex B is 2 plus 2, 4. That is we say that is a blunder in this graph theory terms. So note this. A strong note is degree will never be equal to in degree plus out degree. In degree is different, out degree is different. And when I say degree, it is always representing the graph is an undirected graph. Okay.
Okay, sir.
Okay. Okay. Let us move a little forward. Let us see what is adjacency matrix.
So
this
it means
adjacency.
degree. 1 second. It means degree we cannot calculate for directed graph.
There is no word called degree in a directed graph.
Okay, fine. Thank you.
Yeah. So let's see what is adjacency matrix. So adjacency matrix is nothing but another way to represent a graph. That's it. So why as we are so data we are converting it into graph. Why is it necessary to again represent this particular graph in another way called adjacency matrix?
That
Any,
we can do some computational steps.
Correct. Correct. That is the main key idea behind this adjacency matrix. See, whenever you wanted to input your graph into machines, you cannot draw the graph and give it to the machine, and machine will never understand that. So instead of that, to provide connection between your machine and you, so you just convert this graph into adjacency matrix and you input the values. So you have arrays. So now there are many languages. In every language there is array, and you can form the list, everything. So you can convert this into matrix kind of thing, and then that graph is nothing but equal to this whatever the graph we have, whatever the graph we have drawn from edges and vertices, which we have on the paper is similar. Not similar, it is equal to that adjacency matrix. The same thing it represents in two different ways. So how this adjacency matrix is to be drawn? So it is actually a table that contains rows and columns basically. So this is this table, or if you guys know what a matrix is, it is actually the matrix. So if you want to know what is matrix is, just go back to the lectures. Professor explained it very simple manner. So matrix is nothing but it contains rows and columns. Now here each row represents a vertex, and also each column represents a vertex. So if I have some 6 vertices in my graph, I should draw this table or matrix such that I should have 6 rows and 6 columns, such that each row represents one vertex and each column represents one vertex. And each entry in this matrix or the table is either 0 or 1. So there is no other inputs. So we will only give 0 or 1 depending upon whether there is an edge between those two vertices or not. So if this particular Aij represents the ith row, jth column entry. So that means you go to the ith row, you go to the jth, in the ith row, you go to the jth value. That particular value or the entry, we say entry, will be given 1 if Ij has an edge in the graph G. So if you have an edge between two vertices, then correspondingly the vertex that represents the row and the vertex that represents the column, you give 1 to that particular entry. Aij will be given 1 if there is an edge in the graph G, or else you give 0. You just fill zeros. Okay. Now, yeah, let us try to compute the adjacency matrix of this given undirected graph. Okay, this is a graph given to us, same graph. Now, first and foremost thing is you draw the matrix or the table and label the rows and columns with vertexes. So this particular first row corresponds to the vertex A. Similarly, row B, row 2 corresponds to the vertex B. Row 3, C, D, E, F. So 6 rows, 6 columns. Now this is AA. Okay, let me give you 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now this 1, 1, 1, 1 is the first row, first column entry. So is there an edge from A to A? So we are excluding loops here. So in our adjacency matrix, the diagonal elements will always be 0. We consider it to be 0 because there is no edge from A to A, there is no edge from B to B, there is no edge from C to C, there is no edge from, likewise, there is no edge from F to F. Now from looking at the graph, we fill this table. So let us start from the first row itself. First row corresponds to an edge from A to B. So is there an edge from A to B?
Yes,
Right? So I will give my entry to be 1. So if there is an edge, I will give my entry value to be 1. If there is no edge, I will give 0. Correspondingly, is there an edge from A to C?
no,
No. So what is the entry I should?
0,
A to D?
no,
See from the graph, there is no edge from A to D, direct edge from A to D. So 0. A to E?
no,
A to F?
yes,
A to F, there is an edge. B to A?
yes, sir.
B to E. This is an undirected, so it goes both
Yeah,
ways.
symmetric.
Yeah. So B to A, okay. B to C?
Yes.
B to D?
No.
No,
B
sir.
to E?
Yes.
Yes, sir.
B to F?
No.
Yes, sir.
FS.
Yes, sir.
B to
Yes,
F?
sir.
Yes. C to A?
A to A, no.
No. C to B? Yes.
Yes.
C to D? No.
No.
C to E?
Yes,
Yes.
sir.
C to F? No.
No.
D to A? No. D to B? No. D to C? No. D to E? Yes.
Yes.
D to F?
No.
E to A?
No.
E to A? No. E to B? Yes.
Yes.
E to C? Yes. E to D? Yes. E to F? No. F to A? Yes. F to B?
Yes.
C. Okay. So this is how the adjacency matrix can be computed if a graph is given to you, and vice versa. If an adjacency matrix is given to you, and if I say it is an undirected graph, you can actually find the graph. You can actually draw the graph. Correct? You can just trace back. From looking at here, you see if A, B entry you are having 1. So that means there is an edge from A to B. Similarly, B to A. So there is an backward, there is an edge again from B to A. So there is an undirected edge between A and B. Likewise, you can draw the graph if I have given you the adjacency matrix. And one more thing, if you see the column, if you see the row or column, see either one of it. If it is an undirected graph, you see this row, and you sum up all the values in this. If you add every value 0 plus 1 plus 0 plus 0 plus 0 plus 1, we are going to get, if you add, you are going to get 2, and this 2 corresponds to degree of this vertex.
A.
Degree of A.
A. Yes, sir.
Similarly, you can see any row. You see row E. If I add all those values, I will get 3. And this 3 is nothing but the degree of, you see, if you compute the degree from looking at the graph, you will get 3. From the adjacency matrix also, you can get the degree of a vertex. And how do you
column wise also it will be?
Yeah, column wise also it will be degree. That is why I said either you, if it is an undirected graph, either you choose column or row, it doesn't matter. And how do you classify whether it is undirected or directed graph? Looking at the adjacency matrices, you see, you try to draw a symmetric line along the diagonal. If you reflect this table around this line, if you get the same table, then that is an undirected graph. So you can see here, this particular graph, if I rotate it 180 degrees, this will go there, that will come here. This will go here, that will come here. This will go here, this will go. So nothing changes, same values will, same matrix or same table I will get. So this is called symmetric matrix. Okay. So if the matrix is like this, then that corresponds to an undirected graph. Now when it comes to, just a second, yeah, I also have the directed case also, I will explain. Okay. This is about undirected graph and adjacency matrix of an undirected graph. So what if the graph is a directed one? How we compute the adjacency matrix?
Lower triangle or upper triangle? Anything, only one exists.
What is lower triangle? No.
Along the
That is
principal
not.
axis?
No, that
Actually,
is not.
that was another case.
In directed case, row corresponds to row vertex, and column vertex. From row vertex to column vertex, if there is an edge, we will give the value as 1. So if there is an edge from the row vertex to the column vertex, that means if there is an edge from A to B, then I will give 1 here. Then my entry will be 1 here. This 1 corresponds that there is an edge from A, from this row vertex to column vertex. So this implies there is an edge from A to B. Okay, you can see here, this is a directed graph. There is an edge from A to B, correct? There is a directed edge from A to B. Now, this row corresponds to the corresponds where my edge starts and where it is. This row corresponds to the outward edges. This column corresponds to the incoming edges. Look at in incoming and outward edges. So there is an outgoing edge from A and an incoming edge to B. So that is why I have given 1 at this entry. Okay. Similarly, in whether it is directed or undirected, there will not be any edges or loops. There will not be any loops. So the diagonal elements will always be 0. Now you see, now let us fill this table again. Is there an edge from A to C?
No,
Now,
sir.
now the direction
No,
also
sir.
important.
No,
From
sir.
A to C. No, right?
No.
There is no edge connecting A and C. So it is 0. AD.
No.
No. 0.
AE.
0.
No, so you can see from A to E,
AF
there is
1.
no edge, direct edge connecting between A and E. From A to F, is there an edge from A to F? Is there
Yes.
Yes, sir. Yes, sir. 1.
Yes, sir.
correct?
Yes,
So
sir.
this is the edge. So this will be given 1. So this entry will be 1. Now see, is there an edge from B to A?
No, sir.
So this
No,
entry is
sir.
from B to A.
No. 0.
So start from B. From B, is there an edge going to A? Direct edge going to A? No. So this is 0. From B to C.
Yes.
From B to C. Yes, there is an direct edge. Yes. From B to D.
No.
From D to E.
Yes.
From D to E.
Yes.
Yes, this edge. From B to F.
No.
From B, now see. From B to F. No.
No.
You can see there is no edge that it goes from. Okay. From B to F, there is no edge. So there is an edge from F to B. This edge is from F to E. This is incoming edge to B, outgoing edge to F. So this should be 0. Similarly, is there an edge from C to A? No. From C to B? From C to B? No.
No.
From C to D? No. From C to E? From C to E?
No.
No. From C to F? No.
No.
From D to A?
Everything
No.
is 0.
From D to B? No. From D to C? No. From D to E?
D to E 1.
Yes, sir.
1.
Yes, sir.
From D to F? No.
No.
Correct. From
Sir.
E to A? No. E to B? E to B?
No.
E to B no.
No. E to C?
Yes, sir.
1. 1. Yeah.
E to D? No. E to D, no. That is D to E.
Yes,
Yes,
sir.
sir.
E to F.
No. Yes, sir. 1.
E to F.
Yes.
Yes. F to A. From F to A.
No.
No.
No. From F to B.
Yes.
Yes.
Yes, sir.
From F to D, there is a. From F to C.
No,
No.
sir.
From F to D.
Yes.
No.
No, sir.
D. From
No,
F
sir.
to
No,
D.
sir.
No. From F to E.
Up to E,
Why?
yes,
Yes,
sir.
sir.
Yes, sir.
Correct. Now this is the adjacency matrix for this given directed graph. You see, this directed graph is not symmetric matrix.
Yes,
Sorry,
sir.
this adjacency matrix is not a symmetric matrix. You can see one here, but there is no one here. So entry ij is not equal to entry ji.
Ji.
Entry 1, 2 is not equal to entry 2, 1. Okay. So that means this is not a symmetric matrix. That means this particular adjacency matrix represents a directed graph. Okay. Now in this case, if you see any row, if you consider any row, and if you add this, you will get 2, and this 2 corresponds to out degree.
Out.
Yes, sir.
Out degree of A. Okay. And the column corresponds to the in degree of A.
In degree.
This particular thing corresponds to the in degree of A. Okay. Simply we denote it like this, in degree of A. So this is just the denotion. So you see, sum is 0. Is the in degree of A is 0? Whether the in degree of A is 0 from the graph? Are there any edges that are coming towards A?
No.
No.
Zero, sir.
Degree is 0. So
Yes,
the
sir.
same thing you will get from adjacency matrix also.
Yes, sir.
Correct. So that means either you give me graph or either you give me adjacency matrix, I can compute the other one. Correct. It is same. Either you give me graph, I will compute adjacency matrix, or if you give me adjacency matrix, I can compute the graph. I can draw the graph. Okay. So yeah. So that is about adjacency matrix in directed graph and undirected graph.
What is it? Is either what? I could not able to understand. Either if we give this graph, we can solve with the other graph.
No, it's not about solving. If I give you this directed graph, I can compute
Okay.
adjacency matrix of the directed graph.
Okay.
If you give me this adjacency matrix, I can draw this directed
Oh,
graph.
either way. Yeah. Okay.
Either way. Yeah. Either you give me any one of it, I can compute the other one.
But here the in degree will be 0.
Where?
The in degree in this matrix, will it be 0?
It is 0, right? In degree
Yes.
of A is if you add up all the column of this particular vertex A, first column, you are going to
Yes.
get 0. That means it tells us that the in degree of this vertex A is 0 and the out degree of this vertex A is 2. So if I have to draw the graph, I should keep a vertex A and I should draw two vertices two edges that goes two outward edges, and there will not be any incoming edges. Similarly, from row 2, row 3, row 4, row 5, row 6 and column 2, column 3, column 4, I can be able to draw backtrace the graph again. Okay. Okay, everyone okay?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So that is about adjacency matrix. And now, so we have seen graph, we have seen how to convert that graph into adjacency matrix because we need to input to machines. So what is the need of adjacency list again? What is this adjacency list and what is this particular need? So I guess in the lecture also professor has explained it in one line.
We remove all the zeros and we simply note.
Correct.
Just to save this.
Just to decrease the work of machine. So if you see here this adjacency matrices, there are lots of zeros and zeros doesn't give us anything. Correct. So this 0, there are many zeros in this. So when a machine starts computing, so it will start from the row 1, column 1th entry. It will scan this, It will scan every one of the entry in the row 1, and then it will go to the row 2, and it will scan every entry in this. Like this, it will scan all the, if there are n vertices, it will scan, it will take n square, order of n square, we say. Time complexity will be order of n square. So that means it will take, there will be n square entries, and I have to go to every entry, and I have to take some inference from it. And finally it turns out that most of them are giving us zeros, and we don't require that many entries. That is why we simplify this adjacency matrix to this adjacency list. In this list, what we try to write down is, we just write down all the vertices in a set notation which are neighbors of every vertex. You see, this is how we write. So what we write is, we write all the vertices in one column, and in the next column what we write is, we write the set of all, we write down the list or set of all the vertices that are neighbors to A. So when I talk about neighbors to A, how do you decide if it is a direct, now this is a directed graph. How do you decide whether it is a neighbor or not? Whether depending upon outward edges or inward edges.
Out degree to that node. A to
So
E.
this confusion has came to everyone.
Yes, yes.
What they did is, they have taken two different lists with respect to in degree and with respect to out degree. Okay.
Okay.
So
To resolve
adjacent.
the confusion.
Hmm?
To resolve the confusion.
To just resolve the confusion. So some said we should consider in degree, and some said why not we consider out degree. And
True,
this discussion happened, and okay, chalo, we will do both.
Yes.
Okay. So this is an adjacency. Now let us compute the adjacency list with respect to inward edges. Okay. So that means incoming edges. So I just write down the vertices, or I write down the set of vertices that actually sends an inward edge towards A. So that means from A.
Nothing.
No.
Okay. Okay. With respect to incoming edges. Okay. If there is an incoming edge to this vertex A, we will find out the vertex. We will find out the vertex which is being sent by, which is being sent. Basically, if there is an incoming edge towards
Will
this
give
vertex,
count, na? Here adjacent list also count. It gives counts only, no?
It counts.
It gives count number of edges, no? It gives list.
No.
It won't count. See, in this particular thing, you just have to check: are there any edges that is coming towards A?
Okay, fine.
Are there any edges that are coming towards A?
No.
In this graph? No. That means there are no neighbors to A.
Okay.
So this is an empty set.
Okay.
Now now we will move to the next row. So this row is B. Are there any incoming edges to B?
Yes, sir.
A and F.
So from A and from F.
And F.
So A and F are neighbors. So we take A and F. From C, so to C, are there any incoming edges?
B.
Yeah.
B
From
and
B
E.
and from E, there are incoming edges to C. And when to D, are there any incoming edges to D?
No.
Zero.
This is an empty
No,
set.
sir.
There are no neighbors to D. For E, are there any incoming edges?
Yes,
Yes,
sir.
sir.
D, F.
B, D, F.
B, D, F.
Yeah, B, D, F. And for F, are there any incoming edges?
A and E.
A and E.
And E.
A and E. So this is the adjacency list with respect to incoming edges. Okay, now you see, I just have to scan, I just have to go to this row, I just have to scan number of incoming edges A has. So if there are two number of incoming edges, I should scan two elements. So there are no incoming edges. I don't need to scan anything. I will just move to the next row. So like this, if you see the time complexity, each row, so if there are n rows, each row multiplied by number of integers of that particular vertex is my time complexity. Correct? So in this row, I will spend time. If I have some 4 incoming edges, I will spend time scanning those 4 vertices. Or else I will move to the next row. If I have only one, see here, I have 2 vertices in this row. I will come to the second row, I will scan these 2 vertices and I will move to the third row directly. No need to scan all other vertices here itself. I just need to scan 2 vertices because incoming edges for B are 2. So first row multiplied by 0, second row multiplied by 2, third row multiplied by 2, fourth row multiplied by 0, fifth row multiplied by 3, sixth row multiplied by 2. So 1 times this is what time complexity. Time complexity is much reduced than adjacency matrix. So in adjacency matrix, in each row you should spend n. You should scan all the n entries. Here you should scan only the number of vertices present in that row. That's it. Okay, I hope I tried to make up a connection between adjacency list and adjacency matrix. So adjacency list is just for simplifying the complexity, time complexity.
Sir, any advantage of the adjacency matrix over adjacency list?
Yeah, just now I said, right? The machine takes lesser time to
So
give you the
advantage of
output.
matrix over list. Is there any advantage of matrix?
If you give the adjacency list to the machine and if you give adjacency matrix to the list, so the machine which you have given adjacency list will give you a better, faster output than adjacency matrix.
Sir, I was asking about the converse. That is there any plus point for matrix over list?
Oh, is there any plus point for matrix over list?
Yes.
So if there is, then this adjacency list might not have come into picture. Is what I hope.
So what I was trying to ask that both for both we are actually studying. So
yeah,
there might be some situations where adjacency list will be less.
Searching for an element, searching for an edge.
Sorry,
maybe it's if it is an undirected graph. Okay, when it comes to an undirected graph, your list may contain your list may repeat like this: FE and EF. Every time this repeats. But in adjacency matrix, if you see the symmetriness, you don't need to worry about half of the entries. You just have to worry about the upper side of the matrix. So when it comes to undirected case, maybe adjacency matrix plays a better role than adjacency list, I guess.
Okay, so in undirected matrix will always be an advantage over the list.
In undirected, yeah, matrix will have a better advantage than list. Okay, I'm not sure. Maybe I just have to go back.
If you want to know, is there any edge between the vertices exist or not, their adjacency matrix will help us.
List can also help us.
List will also help us. Correct.
But I think that matrix is better in that case. It will directly go to AIJ, right? And
Search time is less.
As it will go to AIJ, In the same way, it will go to A here.
Okay. Okay.
Actually, in adjacency list, we'll have to scan all the neighbors of I, right? So it's somewhat expensive compared to the matrix.
True. What she told is true. That's the same sentence told in CT.
Yes.
Okay.
In videos also,
Yeah.
it was said that this is the advantage that we get if we use
Correct.
adjacency.
Maybe that is one better way of looking into. See, these are all sets. So once you are coming into this row, you should scan all the vertices that are neighbors of it. Okay. In an adjacency matrix, you no need to. You just directly go to ijth entry.
Means if for a particular edge, adjacency matrix will be an advantage.
See, from matrix here, you see, if I ask you, is there a directed edge from B to C? From B to C, is there a directed edge from B to C? You just have to scan the
B and
Bth row, Cth column.
Cth column.
Just this entry, you just need to scan. Okay. When it comes to adjacency list, if I ask you, is there an edge from B to C? When we compute this, let us compute this first. Okay, I will discuss it. With respect to outgoing edges. So what is this? So that means from
B
A,
and
Two.
is there any edge that
B and F.
E and F.
Yeah, BF. This is C, E. So there is an edge going from B to C, B to E. So C and E are neighbors to B. So similarly to C, it's empty set. For D, it's E.
E.
For E, it's C.
C.
For F, it's
For E,
For
F.
E, F also there.
for E, F also.
F also there.
For F, it is E and B.
B and
E
E.
and E.
Now see, if I ask you, is there an edge from B to C? So what I have to do is, I have to go to B row and I have to scan all the elements inside that set. If I find C, then I say there is an edge from B to C. If I didn't find an edge, if I didn't find the vertex C, then I say there is no direct edge from B to C. So this requires scanning of all the vertices which are present in this set.
Yes, sir.
Okay.
So one more thing, sir. If it will be a question of that how many connection it have, then again list will be an advantage. Na?
How many connections it have?
So again list will be an advantage then.
Both works, right? Adjacency matrix also works pretty.
Sir, matrix will also work, but in matrix, suppose it found one, then after one, it will go on, because after that another one can occur anytime. So from start to end, it has to travel the whole row. But for the list, suppose there are two elements. So
correct. I got you. So it's sufficient to calculate the cardinality of this set.
Yes.
So sir, so in a nutshell, can we say that for a particular edge matrix will be an advantage, but for a list or for the total edges, a list will be an advantage.
Maybe. See, these are some conclusions you can draw if you are able to intuitively see what is happening. Then these are pretty straightforward conclusions you can draw.
It totally depends on what objective we are trying to achieve from this entire thing. So if our objective says description of something, then I believe somewhere list would be advantageous, and if it only wants the program to run faster, then the other way around. So depends on the objective what we are trying to achieve from this.
This is everything related to the cost and time.
Yes, correct.
Yes.
Okay. Okay. Anyway, so this is adjacency list. So adjacency list for a directed graph is written in two different ways. One with respect to incoming edges and another with respect to outgoing edges. Okay. Usually we will represent with outgoing edges. So this is usual list denotation. So even in the lecture, I hope sir has discussed with respect to outgoing edges only.
Yes, sir.
Okay. Yeah.
But it's
So,
pretty clear with your explanation.
Yes, sir. Simple.
Sir.
okay. Thanks. Okay, so that is about adjacency list. Now let us see what is BFS and DFS. So BFS and DFS both, these all are strategies to explore the graph. So if you wanted to explore the given graph starting from one vertex, either we use BFS or DFS depending upon the situation we are in and the strategy which we wanted to apply. So basically, if you wanted to explore your vector, your graph level by level, so that you can able to find the distance, minimum distance from the node vertex to every other vertex. If you willing to find the shortest path also, shortest paths or shortest distance from your node vertex or the starting vertex, then BFS is useful. If you are not willing, you just wanted to find whether the reachability conditions or no, if I start from this node, if I able to reach that particular vertex or not, then DFS is more useful. So depending upon the condition or the question, we use different strategies. So actually, how this works is, okay. Let us do BFS. So for suppose if a graph is given to us, this is how it approaches BFS or this strategy works. So first and foremost thing is we fix the root vertex, or we say just node. Starting vertex, we say starting vertex. Or we say explored vertex. So fix one thing. We say starting vertex or root vertex. So this is a standard notation. We say root vertex. We fix a root vertex from where we actually start to explore. So if you have given a big graph, so you have to you wanted to see how the graph is, and you wanted to go look at the graph in detail, what all the edges are present in the graph, where one edge is connected to another edge, is there a path between two vertices. You wanted to explore this graph. So in order to explore, you should start from one vertex. So that particular vertex you should fix and fix it as a root vertex. You say u or something. So once you fix u, what I do is, after fixing u, I also say this particular u as visited. I just mark this particular vertex u as visited vertex. So mark u as visitor vertex. Now the next step is we explore all the neighbors of the vertex u. Okay, what we do is, once we fix this root vertex and after marking this vertex u as visited vertex, now what this visited vertex means, we have explored the vertex u. That is what it means. Once after exploring this, next we explore all the neighbors of vertex u. And later what we do is, we take one vertex among all the neighbors. So we take one vertex among all the neighbors u. So if I have three vertices, three neighbors to u, I will choose randomly one vertex. And now I mark. So take one vertex, so let's say V. So now what I do is mark V as visited. Okay. Now once V is visited, what I do is, so we will do two things here. One thing is we explore all the neighbors of V. Do we explore? Just a second. Okay. Okay. Mark. So we explore all the neighbors of vertex U. Now what happens is, once you explore all the neighbors of vertex U, yeah. Once you explore all the vertex U, you also mark all the vertices you explored as visited vertices. Okay. So this comes in below. This goes above. So mark all the visited, all the neighbors, of U as visited. Now we take one vertex V among all the neighbors of U. Now the same process we repeat. Now you take vertex V. Now what we do is we explore all the neighbors of B and mark them as visited. Okay. Now move to another vertex which is apart from V. Move to the another vertex U. It's better not to write the statements. Let me take an example and explain.
Yeah, it's better take a graph and draw. That's better.
Correct. So there are lots of steps involving and writing all the steps.
Yes, it's take too much time. Take a graph and explain BFS and DFS.
Correct.
Yes.
So let me take an undirected graph. Let us take this graph. Okay. So okay, I wanted to explore this particular graph starting from the vertex A. So I will take vertex A. I will take this vertex A in my BFS tree, and I will mark this vertex A as visited. So once I mark this vertex A as visited, I will explore all the vertices that are adjacent to A. So there is B, there is F. So there is B, there is F. So we explore, we draw this BFS tree like this. So this is the first level by level. So BFS actually explores the graph level by level. So this particular level is called level 0. That means distance from vertex A to vertex A is 0. This is level 0. In the level 1, all the vertices that are neighbors to A will come. So the neighboring vertices of A are B and F. So there are only two edges, that goes to B and that goes to F. So only two vertices will fall in the level 1. So level 1 denotes that whatever the vertices are there in the level 1, those are actually one distance far from the vertex A or the root vertex. So in terms of edges. So you see here, in order to reach from A to B, I should take only one edge, that is AB. So one edge. So the distance from A to B is 1. And the distance from A to F is also 1. So I require only one edge. So B and F comes in the level 1. Now what I do is, I will take randomly one of the B and F. So I take B, I give this as visited, and also F as visited. Now once I take B, I will explore all the unvisited neighbors of B. Now unvisited neighbors of B are E and C. So the neighbors of B are A, F, E, C, but the unvisited neighbors of B are only C and E, because F and A are already been visited. So A, B, F are already been visited. Those are present in our graph, BFS graph. This is just the BFS tree. Okay, so the unvisited neighbors are only C and E. So we will explore C and E. So that means this particular C and E comes in the level 2. Now I say this particular C and E are also visited. Now I go back to F and I will check, are there any other vertices that are adjacent to F and unvisited? Are there any other vertices which are unvisited and those are neighbors to F?
No. No, sir.
No, right? So we will move forward. So A, B, F are done. We will move to C. So are there any vertices, unvisited vertices that are neighbors to C?
No, sir.
No, sir.
No. So we will go back to
E.
D.
So are there any vertices?
Yes, sir.
Yeah, one is there, D.
Oh, A, D.
So we will mark this as visited and we will add that vertex here. Now you see this falls into level 2 and this is level 3. So this gives us, this BFS tree actually gives us the distance, shortest distance from the root vertex to every other vertex in the given graph. You can see from A, so the distance between A and B is 1, the distance between A and F is 1, but the distance between A and C is 2, and the distance between A and E is 2. You can see the shortest distance from A to C is from A to B and B to C. So that is the shortest distance I can travel from A to C. Okay, similarly to E, from A to B and B to E is the shortest distance from A to E. Shortest path, we can say. So that is why this C and E comes in the level 2. And finally to D, it takes 3 edges, minimum 3 edges from A to reach D. So this is the advantage of BFS tree. From BFS tree, you can actually find the shortest paths from the root vertex to every other vertex.
Is there any rule to choose the level 0 vertex, or can we choose any vertex at random?
See, most cases we will choose the root vertex. We will give you the root vertex. You start exploring the graph from vertex A, from vertex C, from vertex B, like this.
Okay, because if we take D as the root vertex, then the scenario would have been totally
Then the
different.
scenario will be completely different. We can draw that BFS tree also. So now D is visited. Now we take D in the level 0. Now we will see the neighboring vertices of D.
Are
So
only
only E is there.
Yes.
So E comes in the level 1.
1.
Now E, I will mark it as visited.
B,
Now
C.
C and B comes.
And B.
Yes, level 2.
Level 2.
C and B comes in the level 2. Okay. So now I can go to C. So C and B visited. This is visited. This is also visited.
Yes.
So I will go to C. I will just check whether there are any unvisited neighbors of C.
No.
So we will move to B.
B.
So if I move to B, there are two unvisited vertices, A and F.
A. Right.
That will come in the level 3. So A, yeah. So everything being, this will come in the level 3. This
So the
gives you,
entire BFS will depend on what vertex we are choosing as the
correct,
root
correct.
vertex.
What vertex we choose as the root vertex. Okay. So from here, what you can draw is, from D, it takes at least 3 edges to go to A. From D, it takes at least 3 edges to go to F. From it takes 2 edges to go to B, 2 edges to go to C. So the shortest path will be 2 from D to C. Shortest path from D to E is 1. So this is BFS tree with respect to root vertex D. This is with respect to A. So these all are BFS trees for this given graph. Okay. So you explore the graph level by level. So you start from a vertex, you explore all the neighbors of that vertex, then you randomly choose one neighbor of that vertex, you explore all the neighbors of that particular vertex, and you move on. You correspondingly move. Okay. So this is about BFS. What DFS does is that is actually greedy kind of thing. If you start from one vertex, so here itself I will explain what DFS is. We start from vertex A. So once you start from vertex A, you choose the neighbor of vertex A, which is B or F. From B, what you will do is you won't explore all the neighbors. You explore one neighbor of A, and you will pick that neighbor B, and you will forget about A. Now from B, you will pick another vertex which is not visited. So you can come back to F again. Okay. So here you are logged. So once you visited F, okay, let me draw in the new case. So I will just show how DFS works, and we will discuss this DAGs, and maybe Vicky will discuss with DAGs and topological sorting in solve with the session. Okay. So I hope I only left those two topics. And if you know directed and acyclic graphs, which I explained in very first lecture of week 10, then directed acyclic graph is nothing but the intersection of directed graph and acyclic graph.
Yes, sir.
So yeah, you can go by like that. And in the lecture also, Sara has explained it very neatly, I guess, very clearly, this topological sorting and DAGs.
Yes, sir.
So see, this is how DFS works. So DFS is actually will be like an 3D kind of thing. It actually goes deep until it reaches to dead end, and it will come back again, and it will again proceed forward. So see, if I start from A, I will start from A. This is how DFS goes. I will say this is I will mark this as visited, and I will choose the neighbor of A, which is B, and I will choose this as visited. Now I am at B. I forget about A. Now I forget about A. I don't worry about what all the neighbors of A. Now I am at B now. What I do is I actually go to another unvisited vertex, which is adjacent to B. So whether it can be F, E or C. So if it is F, then I will choose F and I will mark F as visited. Now from F, you see there are no unvisited vertices that are adjacent to F. Now again I came to a dead end. I will go back to B. So from F, I will go back to B. And from B, I again choose another vertex. Choose another unvisited vertex. There are two unvisited vertices, C and E. I will randomly choose any one of it. I will choose C. So once I choose C, I mark it as visited. So now I am at C again. I forget about B. So suspend B. Now you forget about B. Now come to C. Now from C, you choose another vertex that is adjacent, unvisited vertex that is adjacent to C. So there is another vertex that is adjacent to C, which is E. So E. And from E, now I forget about C. Now from E, I will look at unvisited vertex, unvisited adjacent vertices
D.
of E.
D
There is
only.
D.
D.
So this is D. So once this is visited, from D I will look at are there any other vertices which are adjacent to D and are unvisited. No. I will come back to E. So there are no unvisited vectors that are neighbors to D. I will come back to E. Even at E there are no unvisited vertices. I will come back to C. Even now there are no unvisited vertices uh, that are adjacent to C. I will come back to B. I will go back to A. So then I will stop. If every vertex is visited, then I will stop. So this is the DFS with the root vertex. Root vertex here. So DFS is actually, you go deep in, no need to explore all the neighbors. You explore one neighbor, you go to that neighbor, you forget about the previous one. From there, you will explore one unvisited vertex which is adjacent to that particular vertex. You go into that vertex, forget about the previous one. Some Gajni kind of thing. Okay. You see the difference between BFS and DFS. BFS tree is actually like this with root vertex A, and DFS is pretty much different from BFS. And this DFS is not level by level. This doesn't give you, unlike BFS, this doesn't give you the shortest path to D. So if you treat it like that, then it shows you like you require 4 edges to reach D. Instead, you can reach D from A with 3 edges only. So this is just the DFS tree. And one particular application in real life also, you will always use DFS only. You will start from when in maze kind of things, or if you start a problem, if I have given you one problem, you will try to solve that problem till end. Once you are unable to solve that problem, you will come back till where you can use another method. You will come back to that step and you will use another method. You will try to solve it. If you are unable to solve it again, and again you will come back above, and you will start from another method, using another method. That is how it works in most of the real life cases also. So DFS is always the greedy approach, and every one of us will use that approach in real life. So no one uses BFS.
Mostly only DFS is used, or you mean to say BFS is outdated kind of a thing?
No, not outdated. In real life, without knowingly, we use DFS. This DFS, not DFS actually. We use this greedy kind of thing. Okay. We don't worry about what the previous is. We worry about one particular path, and we go into that path. Once you are sure that you cannot go anywhere, then you will come back. So you will come back a little back. You will come back a little, and you will again move in the different direction. Even in maps also, you see, if you wanted to travel from one city to another city.
Right. So during planning a journey, this kind of graphs DFS could be used. But then when you plan an event, or maybe I believe some kind of a big event is planned, there BFS could be better, so that we know where is the exit and from which level the exits could be.
I don't say BFS doesn't have an advantage over DFS. BFS also has an advantage over DFS. But what I wanted to mention is, in real life, most of the times we tend to follow DFS approach rather than following DFS.
As in the beginning of the session, when we were talking about accessibility, then we were doing that hit and try.
Little louder, please. Little louder. Abdullah, can you be little louder?
As in the beginning of the session, when we were talking about accessibility, so we were doing that hit and try, but following a path, and that example in the beginning of the session.
Yeah. Following a path. If you are unable to find the path, you will press. Yeah, correct. So just go back and watch this BFS and DFS. We will again come in this solve. I didn't mention most of. I didn't spend more time on DFS and BFS because again you will get it on solve with the interactive kind of thing. You will be seeing some few slides which actually discuss this BFS and DFS. So come back on March 18, which is on Friday, I suppose. There maybe we will discuss solve with us as well as this DAGs and topological sort. Okay.
Yes.
Okay.
Thank you very much.
With
Very
that,
nicely
yeah.
explained all the concepts.
Thank you, sir.
Thanks
Thank
a
you,
lot,
sir.
and yeah, have a good
Thank you, sir. So one more thing. Last
Thank you, sir. Thank you.
Thank you.
Yeah, thanks a lot.
Thank you, sir.
Yeah, thanks a lot.
Sir, can
Sir.
you just share the PDF?
This particular PDF. Huh?
Yes, sir,
Yes,
please.
sir.
It's
Okay.
very helpful.
Okay, I will apply.
Sir.
Thank you, sir.
Yeah.
Thank you, sir. Sir, can you spare a minute or?
Yeah, sure. Some 5 minutes for casual
yes,
doubts, like normal.
yes, sir. Yes, sir.
Yes,
Sir, this is regarding the differentiation. I mean, limits, sir. Continuity of the differentiability of the function. For example, if f of x is known to be differentiable, and let's say that f of x is equal to e power x when x is less than 0, and let's say that f of x is 1 when x is equal to 0, and f of x is equal to e power x when x is greater than 0. And at f of x is equal to 0, let's say that it is continuous and differentiable. And just as, I mean, does it mean that f dash of 0, when we differentiate e power x, and when we differentiate that, I mean, is it okay? I mean, instead of doing the limit thing.
Correct. So yeah, if it is differentiable, you are sure, right? Now you are sure that it is differentiable everywhere. So this particular function which you have defined is different from the function f of x is equal to e power x on whole r.
Okay.
Okay. So that is different from this.
Okay.
Is
And
that in quiz 2 question are you asking?
Yes, ma'am. I don't remember.
I also did f dash 0 only because I was unable to find that limit.
I was able to.
We'll get the same answer.
Which one is this?
In quiz 2, PQ question is there, na PQR. Find
Yes, sir,
PQR. For that R, not to get R, I also tried differentiability formula f of a plus h minus f of a by h, but I don't know, I couldn't solve, so I simply did f dash 0 and I equated LHS and RHS equation, I got R.
Yeah, you will get.
Excuse me, sir. But sir, there was a mistake in that question.
Yes, sir. It's
yeah,
less than
yeah,
0. Yes, sir. In the question, it was given less than 0 for two of the conditions.
Right. In the start of the session, I just pointed out this. We are looking into that. In the set 2 people, you got x less than 0.
Yeah.
We will try to do something regarding that. And we that error we have seen. Okay. So that is not your mistake. That is a mistake from our side. So we will take it into the consideration.
So that is allowed. No. So differentiating and getting the value is allowed, no? Instead of doing the limit thing.
Yeah.
Okay.
You will get the same.
Okay.
Sir, a small doubt from revision session. Of Qs 2. In the composition of two functions, there was a question. Question number 2 exactly. Fx equals to under root x minus 1 and gx x minus 1 and gx equals to e to the power x square plus 2x.
X square?
Sorry, x to the sorry. e to the power x square plus 2x.
Oh.
Plus 2x.
Plus 2x.
Yes. So in this